Hey, check it out, everybody. Who's seen this before? Okay. Euler's identity, known as the most beautiful equation in mathematics. I'm going to slip in things like this from time to time. This should take your breath away, people. Okay? It looks really, really nice, even if you have no idea what any of it means. Okay? It looks really, really simple. Okay, look at what's involved here. You have exponentiation, you have addition, you have equality. Okay? And you have multiplication. Okay? So the big important operations are all there. Big important numbers are all there. You don't need to know this for the course. Okay? In fact, this number doesn't exist in this course. Okay, you've got 0. The number, if you add anything to 0, you get the number back. You've got 1. If you multiply 1 by anything, you get the number back. E, we've talked about a lot as the natural base of the exponentials and the logarithms. A transcendental number and a rational number. We've talked about pi, obviously the ratio of the circumference of a circle to its diameter. Again, a transcendental irrational number. Okay? And there's no reason to think that these two would have any connection. I, which again does not exist in this course, the square root of -1, which does not exist in this course. Okay? The square root of -1, the unit of the imaginary numbers. Okay? All fundamentally important numbers, and somehow they all come together in this one beautiful, lovely, simple equation. Okay? I'll talk more about that later. But just for now, go. Because that's amazing that that works that way. Okay? There's no reason to think that that should happen, and yet it does. And that's how it must be. Okay? You do not need to know that. Okay, gang. 3 little enrichment bits today. This is one of them. You may remember this. I brought this up in class once, and I said I might bring it up again. So very briefly, I'm going to take you on a tour of something. Remember, in this course, you can't take the square root of a negative number, but other people often do. And I is the square root of -1 for people who are allowed to use it. Okay, and I showed you this, and I said it was the most beautiful equation in math, Euler's identity. It's got a bunch of fundamental constants. It's got all the fundamental operations. It brings E and pi and I together in a weird way. And it's simple looking, right? It should be beautiful just on sight. And I didn't explain to you where this came from, so let me just show you where this comes from. Okay? That first equation is just a special case of this mad thing. Okay? So if you go e to the square root of -1 times something, you get this stuff. Okay? And that's how it has to be. There's no other way to make anything work. And you can prove this using series, or you can prove this using derivatives. Possibly, we should be able to do it using the stuff from this course. And this should be amazing because of this, right? The exponentials we've seen, okay, when we've got only real numbers, are either growing or decaying. Okay? And yet, where we throw the square root of -1, and their magical stuff happens, and the damn thing becomes periodic. Okay? That's crazy. Okay? So something we're used to having go like this or go like this, now does this. It oscillates. It looks like sines and cosines. And this is fantastically useful. So when you want to deal with waves, as a lot of people do, you can use exponentials, which are friendlier than sines and cosines, and so you can just deal with exponentials when you want to deal with waves, and it makes life very, very easy. And a lot of people use this. So don't let imaginary fool you. Use numbers to model things, and imaginary numbers are no different. They make life easy for people who deal with these kinds of things. Nope, I won't say that. You may remember this from a previous tutorial. We talked about the hyperbolic functions up there, and I said if you know something about complex numbers, those equations may look familiar, and this is why. Using Euler's formula, you can write sine and cosine, normal sine and cosine, in terms of complex exponentials like that. Okay? And that looks a hell of a lot like the hyperbolic function definitions we saw. Okay? Lesson being, if you can talk about complex numbers, if you can talk about imaginary numbers, you broaden your horizons, you get to do a lot of stuff, possibly more easily than you would without them. But in this course, they don't exist. Okay.